Welcome back, Focus Learners, to today's Explainer. Today, we are looking at a technological shift that is frankly completely rewriting the rules of the future. We're talking about the state of quantum computing in 2026. Now, for decades, quantum was treated as this fascinating but super distant theoretical physics experiment. But as we're going to see today, we have officially crossed a massive tipping point. Quantum has graduated from the academic laboratory into a full-blown industrial reality.
Okay, let's dive into this with a number that sets the stage perfectly. $12.6 billion. That staggering figure is the unprecedented amount of venture capital poured exclusively into pure-play quantum startups in 2025 alone. That is a massive 6.3-fold increase over the previous year. I mean, this kind of money doesn't just fund research papers, right? It builds factories, it builds supply chains, and it's jumpstarting completely new industries from the ground up.
Section 1, the Quantum Gold Rush.
So we have completely left the speculative research phase in the rearview mirror. This is now a multi-billion-dollar industrial and geopolitical race. And to really grasp the scale of this race, we have to look way beyond just private venture capital. By early 2026, cumulative public government commitments to quantum initiatives actually surpassed $60 billion globally. Governments around the world aren't just handing out general research grants anymore. They're taking direct equity stakes in companies and building physical foundries. They're treating quantum computing as absolutely critical sovereign infrastructure, much in the same way they view energy grids or telecommunications.
Now, what's really interesting about this slide is the global distribution of the players who are actually building this technology. The European Union is currently leading in pure density with 173 active pure play startups, which is strongly supported by their deep academic foundations. Right on their heels is the United States with 164 startups. But it's worth noting, the US is the dominant force when it comes to venture backing and actual commercial deployment. We're also seeing major hubs popping up in Canada with 59 companies doing amazing pioneering work in hardware and photonics, and the UK with 56 companies acting as a massive hub for private financing. It really is a truly global ecosystem. However, as this landscape matures, we're seeing some rapid structural consolidation. The rate of brand new startups is actually declining right now. Why? Because capital is concentrating into the established leaders. These big players are aggressively verticalizing to secure end-to-end control of their supply chains. A prime example of this is IonQ's definitive $1.8 billion agreement to acquire SkyWater Technology. They are doing this to onshore their supply chain and secure a trusted manufacturing foundation, essentially transforming themselves from a software and design firm into a vertically integrated hardware powerhouse.
Section 2, breakthroughs and the Willow chip.
All of this incredible financial movement is being driven by monumental leaps in the physical hardware itself. So the crucial point is understanding what Google's Willow chip actually achieved in December 2024. They demonstrated what's known as below-threshold error correction. For years, the big problem with quantum computers was that as you added more physical qubits to make the computer more powerful, you inadvertently added more noise and more errors, making it worse. But with Google's 105-qubit Willow chip, they finally crossed that break-even point. By grouping physical qubits together into what's called a logical qubit, they proved that a larger surface code actually decreased the error rate, meaning the encoded logical qubit essentially outlasted its best individual physical components. Guys, this is literally the holy grail of fault-tolerant computing.
And the performance leaps, they're just breathtaking. In October 2025, using that Willow chip, Google ran the Quantum Echoes algorithm. It tracks how information scrambles through a quantum system, and it did it roughly 13,000 times faster than the best classical supercomputer estimate. Most importantly, this wasn't just some theoretical claim on a whiteboard. It was a verifiable quantum advantage that could be reproduced and cross-checked on other high-quality quantum hardware.
Section 3, the architecture wars.
No, Google's way isn't the only way. We are currently right in the middle of a massive engineering battle between competing physical qubit modalities. And this brilliantly illustrates that we actually still don't know which physical hardware strategy will ultimately win. You've got superconducting qubits used by Google and IBM. These are super fast, capable of deep circuits, but they are highly sensitive and require cooling to near absolute zero. Then you have silicon spin qubits, championed by companies like Intel and Dirac. These are incredibly promising because they're highly scalable. They use the exact same standard COO manufacturing as the chip sitting in your laptop right now, and the goal is to pack millions of qubits onto a single chip. Finally, there's the topological approach pursued by Microsoft. This one is high risk, high reward, using exotic materials with built-in native error protection right at the physical level. So with all this momentum, billions of dollars in funding, and incredible physics breakthroughs, what could actually stop the quantum revolution?
Take a second and really think about it. What usually breaks a cutting-edge industry? It's not usually the theory, right? It's the harsh physical reality of actually building the machines.
Section 4, severe supply chain bottlenecks.
Yep, the biggest threat right now isn't a lack of funding or bad code. It's physical roadblocks. As these quantum chips transition from low-volume lab prototypes into commercial production, they rely on some downright bizarre, highly fragile, single-source dependencies. For example, if you're building those highly scalable silicon spin qubits we just talked about, you need an exceptionally clean magnetic environment. Natural silicon just won't work because it contains silicon-29, which causes magnetic noise and destroys the quantum state. So you have to chemically strip the silicon-29 out to get pure isotopically enriched silicon-28. And doing that requires highly specialized gas centrifuges that are historically located in very few places globally. It creates a massive single point of failure in the supply chain. And it's the same story for photonic architectures, which are heavily dependent on highly specialized optical crystals like lithium niobate.
But honestly, perhaps the absolute wildest dependency is helium-3. To keep superconducting and silicon spin processors at thousandths of a degree above absolute zero, you need dilution refrigerators, and those rely on helium-3, which is an exceptionally rare isotope that basically doesn't exist in nature in harvestable quantities. So where do we get it? It is primarily produced as a radioactive decay byproduct of tritium, which is used in nuclear weapons programs. It's a tightly regulated, incredibly constrained resource. So yes, the future of ultra-fast computing literally relies on harvesting the byproducts of nuclear weapons just to keep the chips cold. You can't make this stuff up.
Section 5. Why quantum matters today. Let's move to and see how this builds into real-world applications right now. Beyond all the wild physics and supply chain drama, what is the actual impact of this technology today? Well, it really comes down to a mind-boggling advantage in energy and sustainability for specific, impossibly complex problems. Let's look at a molecular dynamics simulation, which is absolutely crucial for discovering new drugs or advanced materials. On a massive classical GPU cluster, a highly complex problem might take 10 hours and consume 3,000 watt-hours of energy. But pushing that exact same calculation to a quantum processing unit, or QPU, it takes just 1.5 minutes and consumes only 25 watt-hours. Sure, the quantum computer requires a ton of power to stay cold, but because it solves these combinatorial calculations in seconds rather than hours, the total energy footprint just drops dramatically.
So, based on all this data, what should organizations actually be doing right now in 2026? First off, avoid vendor lock-in. Because we still don't know for sure if superconducting, silicon, or topological will win the race, you should use cloud platforms like AWS Braket or Azure Quantum to test your algorithms across all of them. Second, invest heavily in hybrid classical quantum workflows. The near future isn't about quantum totally replacing classical computers. It's about using quantum chips as highly specialized coprocessors to handle the insanely complex subproblems while your classical GPUs do the heavy lifting for everything else. And third, and this is without a doubt the most urgent, implement post-quantum cryptography roadmaps immediately.
That last point is absolutely crucial because of an immediate cybersecurity threat known as harvest now, decrypt later. Look, fault-tolerant quantum computers that can break modern public key encryption might still be a few years away, but bad actors are already vacuuming up and storing heavily encrypted, incredibly sensitive data today. They are hoarding it right now with the specific, targeted goal of decrypting it the second a powerful enough quantum computer comes online tomorrow. So I'll leave you with this. Is your encrypted personal or corporate data already sitting in a malicious vault somewhere, just waiting for a quantum key to unlock it? Because the billions of dollars rushing into the space practically guarantee that the key is being forged right now. This quantum revolution isn't just about getting faster calculations. It's about fundamentally altering global security, material science, and geopolitics as we know it. Keep learning, stay curious, and please protect your data.